Hi, this is a review lecture. The topics are right here on the screen. It's going to be properties of graphs that you can get from the derivatives, and then also the techniques for graphing, for drawing those graphs. And then after that, optimization problems. So we're gonna just do a few problems involving each one of these topics. But first, a very brief recap, the important properties that we should know. Important properties regarding graphing and regarding properties of functions you should be aware of these properties right here. When the derivative is positive on a certain interval, that means the function is increasing, going up. When the derivative is negative, that means the function is decreasing, going down. And regarding the second derivative, when it is positive, that means the function is concave up. When the second derivative is negative, the function is concave down. So what about locations where those guys are equal to zero, either the first or the second derivative? Well, instead of saying equal to zero, you should really focus on where the behavior changes. Maybe points where the first derivative goes from positive to negative, for example. It doesn't mean necessarily that it's going through the number zero right there. So this is the correct way to think about this type of thing. If the derivative changes sign around the point x, then x is going to be a local extreme point. You can imagine either a derivative going from positive to negative, but maybe at that point the derivative itself does not exist, like a sharp corner right here, a cusp. But regardless, this point is a local extreme. It's a local max in this case. And then similarly, if the second derivative is changing sign around the point x, then x is called an inflection point. Imagine a function that has a positive second derivative up to here, and then it becomes negative. So then it becomes concave down. This point right here, this x value would be an inflection point. But be careful, it's possible that the derivative or the second derivative are equal to zero without the point being an extreme or inflection point. Usually we want to find these locations where the derivatives are zero only because we are actually interested in the locations where they are positive or negative. All right. Now there are certain derivative tests that we should be aware of. The first one, we basically just mentioned it. If you have a point A such that the derivative is negative for points smaller than A and close to it, and the derivative is positive for points larger than A and close to it, then this A must be a local minimum point. And similarly for local max, you just change these signs here. The derivative was positive before and then becomes negative after. But look at this remark down here. The derivative itself at the point A doesn't need to exist. But in that case, as long as the function is continuous up to this at this location A, then this test still works. So this is just the situation that I had just drawn up there. A function whose derivative is positive before a number A and then negative afterwards, even though it does not exist at this A, but as long as the function is continuous there, which it is in this case, you can conclude this must be a local maximum. That's the first derivative test. Second derivative test, first of all, it's important that you are at a critical point where the derivative is zero. So you're talking already about an A such that f prime is zero. If that happens and you're able to look at f double prime, then the test works like this. If f double prime is negative, A must be a local maximum. That's easy to think about, right? Because if f double prime is negative, that means around this point A, the function is concave down. So that means it's a local maximum. Similarly, if you're finding a positive second derivative, that's going to give you a local minimum. If you find the number zero, the test is inconclusive. It could be anything. And this test can only be applied if the f double prime function is continuous, but that's usually the case. Anyway, we basically never have to worry about this part. Important thing to notice about these tests, they always allow you to classify points as local. You're never going to be able to justify a point being a global min or max just by using the tests. The tests may help you, but if you're required to justify your answer, and we're going to see how, usually you're going to need, if you're talking about global points, global max, global min, you're going to need to use some more work. Okay. So here's the first problem that I have for this topic. What do the first and second derivative tests say about the critical points of a function f whose derivatives are given as follows? And also assume that f of 2 exists. So I'm not giving you the actual f, I'm just giving the derivatives. You can try to differentiate this f prime to see that you really do get this f double prime here, but we don't have to. The function, the problem is giving that to us. So first of all, what are the critical points of this function? F prime equals 0 at x equals 1 and minus 1. That's very easy to see from here. And also it does not exist at x equals 2. Remember that this is what critical point means. Either f prime is 0 or does not exist. So we're going to need to analyze this function at those three locations, those three critical points. First, let's use the first derivative test. First derivative test. According to this test, what we have to do is understand the sign of f prime both before and after each one of these points. Now look at the f prime function. It's a function of this particular form where you have product as well as quotient between three separate functions. The x minus 1 to the 4, x plus 1, and x minus 2. All those three locations, the 1, minus 1, and 2, they are possible transition points. They're locations where this function might change sign. So instead of just plugging in particular numbers around those guys, here's one thing that you can do. So imagine here is the real line with those 3 points marked on it, minus 1, 1, and 2. Let's analyze separately each one of the pieces that appears in f prime. X minus 1 to the 4, x plus 1, and x minus 2. Analyze the sign of each one of these guys separately in each one of the 4 locations that we have that are determined by these transition points. That's going to be very easy to do, right? First of all, x minus 1 to the 4th never changes sign. That's always positive. X plus 1 is going to change sign at the number minus 1. It's negative before it and becomes positive afterwards. Similarly, for x minus 2, it's going to change right here at the number 2. Those are very easy to analyze. They're just linear factors. So what does that mean for your f prime? F prime is just a product or quotient involving all these three functions. It's just like thinking about the sign of it. It's just like thinking about the sign of the product of all three. Basically, when you have plus times minus, or divided by minus in this case, this is going to give you a plus. The minuses cancel each other. This one has only one minus, giving you a minus. Similarly here. And this one, plus plus plus, gives you plus. So this is the behavior of f prime around each one of those points. So when you look at the behavior of f around those points, let's look, for example, around the number minus 1. It is initially going up because of this plus and then starts going down. The graph of f looks kind of like this. Here, it's going down and remains going down. It's like this. Or, well, one is a point where the derivative is 0, so it's more like the derivative becomes 0, it becomes a horizontal graph, but then it keeps going down after. And here, going down and then up. This is the behavior of the graph of f around those points. So you can see from here that minus 1 is a local minimal, sorry, maximal, because this is like shaped like a peak. This one, which is the point 2 is local max. Sorry, I keep saying the wrong word. Local min. because this is shaped like a valley around that point. But here, the number 1 is neither local min or max. The function is not attaining a locally largest or smallest possible value around that point. It just keeps going down through it. This is the first derivative test. Allows you to classify all 3 points. Let's now look at the second derivative test, because the problem was asking us to do both. Remember, the second is usually not as powerful as the first. This one is not going to allow us to reach as many conclusions as the first one. But whatever we can, it should at least be the same conclusions as the first one. So first of all, second derivative test can only be applied at these 2 points, 1 and -1, not at the point 2, because the point 2 did not have this property, f prime of x equals 0. Rather, this was a point where the derivative did not exist. So we cannot even apply the second derivative there, right? So only those 2 points are going to be able to, we are going to be able to apply that. What we have to do is look at f double prime. Here is the formula. Calculate it at each one of those points, 1 and -1. F double prime of 1 and -1. What you're going to see, for 1, that's very easy. There is a factor of x minus 1 to the third in the formula. So this is giving you a 0, which means test is inconclusive. Unfortunately, this test does not tell you anything about this point. We already know it is actually a local, what was it? Oh, it was neither, right? In this case, here it is. It could have been max or min. This test would not know. But at the number -1, that one you can compute. Just plug it into the function. You don't actually need the value. You just need to understand what it's going to be in terms of positive or negative. Do it yourself. You're going to see a negative number showing up. When you find a negative, that means the point is a local max. Negative for max, positive for min. So at least this one is the same conclusion that we had from before. Only one of them is only one of these 3 conclusions is the one that we can get from the second derivative test. So it's an easier test, but less powerful. But that concludes this problem. Let's move on to another. Drawing graphs. So yeah, I just have a couple more remarks to give you about drawing graphs. You're going to see many problems that ask you to either draw a graph or select from a few options. What is the graph of the function f? These are the things that you have to keep in mind. You don't always need to do all of these things. That's going to depend on the situation. But they could be important things to do. Finding transition points, which are the points where the derivatives are equal to 0 or does not exist, because that helps you study the sign of these derivatives in between those points, which is going to give you increase, decrease, concavity, all of that. Find the value of the function on those transition points, just so you know where to put the height of the function when you are at those points. Y-intercept is very easy to find. It's y equals f of 0. X-intercept can also be easy to find, just solving for f of x equals 0. So you know where the graph intersects the x's. Now, if you have some point A that is not in the domain of the function, like just in the previous situation where we had x minus 2 in the denominator, analyze the limits as x approaches this A, both from left and right, in order to understand if there are any vertical asymptotes. By the way, this limit notation here, this is the same as writing the x converging to A plus minus straight down, like this, straight below the symbol of limit, or more like this as a sub index like this. This is the same thing. You may see this type of notation here. That's the same thing. So okay, and then finally, horizontal asymptotes. If by any chance you need to understand the behavior of the function when x gets large in absolute value, which means both on the positive and on the negative side. So also analyze limits as x goes to infinity or minus infinity. Those are all things to keep in mind when you're drawing graphs. Here's a problem where I'm not giving you a function, I'm giving you the properties and asking you to draw. Sketch the graph of a function satisfying all of these properties. There's a huge list here. I really encourage you to write these down because I have written them down here on my paper. I'm not going to be scrolling back up all the time to come back to these guys. But you see they're giving you f is differentiable at all points except at x equals 2, where there is a vertical asymptote. Y equals 1 is horizontal asymptote. I'm also giving you the only points where the derivatives are 0. -1 and 4 for the first derivative, and -1 and 6 for the second derivative. I'm giving you the intervals where f prime is plus or minus, as well as the same thing for f double prime here. And I'm also giving you the value of the function, well, not the value, but the sign at those transition points. Remember the locations where either f prime or f double prime were 0. I'm telling you the value of the function is either positive or negative at each one of those. So draw the most accurate possible graph for this and then answer. We're going to have a few questions here. We'll worry about those later. Okay, so let's get to this graph. There were transition points at -1 and then 4 and 6. The question also said, by the way, the function is not differentiable at the number 2, where there is a vertical asymptote. Now 4 and 6 were transition points. Remember the signs of f of -1 was positive, so I'm going to put some positive number here. It was negative for 4 and also for 6. The function, the problem, by the way, also told us the derivative, the first derivative is positive on this interval between 0 and 6. So you see that I already drew this point for 6 slightly above the point for 4 because the function is going to be increasing here. So, you know, this type of detail, it's things that we can determine. What else? Y equals 1 is a horizontal asymptote. They told us that. Now, we don't know yet if this is going to be an asymptote for x going to infinity or x going to minus infinity, or both. You know, any one of these things could happen here. We don't know yet, but we're going to be able to determine that. Okay. What happened at locations where the first derivative was 0? Those were -1 and 4. So at these locations, we are going to have horizontal tangent lines. This one, on the other hand, the x equals 6, this was an inflection point, as well as x equals -1, that was also inflection. The concavity changes at those points. Now let's just look at those concavity and also increase versus decrease. For example, they told you that the function is increasing between -infinity and 2. So all the way here, in this location, the function should increase, with the concavity being, what was it, negative here and then positive here. Negative up to the number -1, then positive between -1 and 2, because -1 was inflection point where the concavity changes. So we have to draw a function of negative concavity before -1 that is increasing this function, and then becomes positive concavity, concave up, if you will, but still increasing. So this is what this function should be doing. Maybe it actually stops at this axis like this, but probably not, because they told us this is a vertical asymptote right here. So this is how we know that the graph, at least if this is going to be the side of it, on which it has an asymptote, then it must look like this. All right, so already from here, we know that the horizontal asymptote is gonna need to happen at x going to plus infinity, because as you're going to minus infinity, the function just keeps going down forever with a negative or concavity pointing down, right? This graph could not possibly try to converge to this line if it has this concavity. Okay, so this is the piece here. And then we're just similar things at this other side of the line y equals 2. The concavity was positive here, if you go back and see. So we know the function looks like this up to the number 6, and then 6 is inflection point. It changes to down concavity. Now the function was decreasing between 2 and 4, and then starts increasing afterwards. So something like this decreases up to this place where it has a horizontal tangent line, then starts increasing again. But look at the concavity. This is still concave up. Now I'm going to change this to concave down. And we know that it must try to converge towards this line y equals 1. That was the horizontal asymptote. So this is the best sketch that we can draw for this graph. There are many problems where you have to do this with a specific function. So nobody's going to tell you, for a few problems, nobody's going to tell you all these properties. You have to determine them yourself and then draw a sketch. All right, let's go to these questions now. Where does f have a local minimum? Look at the graph. There's only one location where there is a local minimum. It's at x equals 4, right here. This is the only valley that you have, even though this is not going to be a global minimum because there are locations where f is strictly smaller than that. But this is a local minimum, x equals 4. Item B, calculate the limit as x goes to infinity. Well, that one we know that we've been able to determine that this is where the horizontal asymptote is. It could not have been here, so this limit is 1. Y equals 1 was this asymptote. The answer is 1. C, what is the sign of f of 0? Positive. Just look at f of 0 is this number right here. So yeah, how did we know that? Well, they told us f of -1 is already positive, and they also told us the function is increasing along this entire region here before the number 2. So whatever this positive number was, f of 0 is going to be even larger than that. All right, so things like that, you should be able to put into words if necessary. A question like this might also ask you to briefly explain how you know. I'm just indicating, but I'm never writing these things down. This is the full answer, full solution to this problem. Now, okay, similar thing to the previous one, but with an actual function. Sketch an accurate graph of this function, x plus 2 sine x, in the domain from -pi to pi. Then answer some questions. Let's sketch the graph first. So right away, just take 2 derivatives if it's easy enough. In this case, it really is. I'm taking the derivatives here. You see that the 1 disappears for the second derivative. Cosine becomes minus sine. And find the locations where those either do not exist or are equal to 0. In this case, derivatives will always exist, but where are they equal to 0? F prime equals 0 is the same thing as cosine x equals -1/2. Think about your unit circle. We are only talking about angles between -pi and pi. Imagine that this is the range of angles that we're talking about. The only locations where cosine is -1/2 is going to be these 2 angles here. They are -3/4 pi and 3/4 pi. All right, and similarly for the second derivative, where is that equal to 0? So you need sine equals 0. What are the angles whose sine is equal to 0? Only you have -pi and pi, as well as x equals 0. And technically, you don't need to include these guys, minus pi and pi, because they are the endpoints of the function. This function came with a domain for us between minus pi and pi. Those are called endpoints, and they're going to be considered in all of our evaluations. So all that we found here, you can call those transition points. It's going to be helpful to have the value of the function at all of them. So minus pi, minus 3 pi over 4, 0, 3 pi over 4, and pi. Go back to your function. The original f, don't plug anything of any of these numbers into f prime or f double prime. Plug all that into f, which is x plus 2 sine x. That's going to give you minus pi and pi for these guys. Now minus 3 pi over 4 minus root 2 over 2. Sorry, not over 2 because it's 2 sine x, so minus root 2. F of 0 is 0, and this one is plus 3 pi over 4 plus 2 times root 2 over 2. So these values, whatever they are helpful to know. Okay, so what else? All right, why else did we find these transition points, the locations where f prime and f double prime are 0? Well, we did that because we want to analyze the sign of the function in between them. Not the function, the functions, the derivative and the second derivative. Because that's going to allow you to have a shape of the graph of f. So take your domain here at the numbers minus pi, minus 3 pi over 4, 0, 3 pi over 4, and pi. You're only concerned about these particular locations. Analyze the signs and everything. That's very easy to do by, once again, just plugging in points or also trying to understand which ones, what are the meaningful points for each one of these guys, like f prime. It's only going to change, potentially, only going to change signs for these two guys, the locations where that function was equal to 0. So you do this analysis. Let me copy it from my notes. You're going to find minus plus plus minus and plus plus minus minus, giving you the general shapes like this for your function f. So just with this, there is already enough information for us. There's nothing like horizontal asymptotes because the function, the domain does not go all the way to minus infinity or plus infinity. There are no vertical asymptotes because the function is well defined at all points. X-intercepts and Y-intercepts, they're going to be not necessary as we are going to determine now once we try to sketch the graph. Here's minus pi and pi. The value of the function was all the way up here, pi and minus pi. Yeah, so the value at minus pi was minus pi. The value at pi was pi. F of 0 is 0, we know that. And then there were these two critical points, minus 3 pi over 4 and 3 pi over 4. Now draw a function with these general shapes going through the points where it goes. You're going to see this. Let me zoom out a little. Okay. Yeah, so for example, one thing that I did not mention, when I look at the value of f of 3 pi over 4, which is this number, that number is a little larger than pi. It's not so easy to figure out. You have to think about this, the math for a while. Root 2 is larger than pi over 4, which means that the combination here will be larger than pi. But we did not have to do that because we also knew, look at the last interval, the interval between 3 pi over 4 and pi. Look at this. The f prime function was decreasing there. So we know the function needs to go down between these, whatever value it has for 3 pi over 4 And the next one, this value for pi, the function is decreasing. So just from knowing that, you're also able to determine that the value here must be all the way up there. So yeah, this is the function. Now we can answer the questions. How many solutions are there to f of x equals 0? Only one. And it's at x equals 0. We can see that from the graph. It only crosses the x-axis one time. And what is the global maximum value? Value, not point. So that means the y value. It's going to be this guy right here, 3 pi over 4 plus root 2. We can see it from the graph. The location where the graph is at the maximum height is right here, corresponding to this point, 3 pi over 4. And the y value here is this one, 3 pi over 4 plus root 2. That concludes this problem. I have just one more about graphing before we transition into optimization. This is a problem about the third derivative. This is going to require us to think a little because we never discussed the third derivative. What does it mean for the graph of a function? The problem is simple. Out of the 3 graphs of functions f shown below, only one satisfies this property. 3 derivatives larger than 0 for all x. Explain why the other 2 cannot possibly satisfy this condition. So when you look at these graphs, what is the one that has the third derivative always positive? Well, the trick to understanding this is by thinking about it this way. The third derivative is the same thing as the derivative of the second derivative, right? You just take 2 derivatives and then one more. So what does it mean for that to be positive? It means that the function f double prime is increasing. A derivative is positive when the function inside is increasing, at least on an interval. But that's the case for all these functions. They are all defined on a domain that can be called an interval. The domain doesn't break at any points. So when you look at these functions, can you try to understand which one has the second derivative increasing? Or rather, we're trying to look at the other 2, right? The problem said, explain why the other 2 cannot possibly have the property. So, you know, the second derivative means concavity. Looking at the graph A, this is right here a location where the concavity is positive. F double prime is positive because we have a smile. But then it becomes a frown later. F double prime is negative. You see that F double prime went from positive to negative. F double prime decreases. If you have a number that goes from positive to negative, that means it's going down. A similar thing is going to be true on item C if you compare only this region here. Similarly, F double prime was positive here and then became negative. So F double prime decreased, at least in this location. Well, so we know those cannot be the graph that we're looking for. F double prime is supposed to be increasing for all points. This is the one, item B here. Here, F double prime was negative at first and then became positive. F double prime increases. So the answer is B. B is the graph that has the triple derivative always positive. And I'm not going to write down the explanation in words here. You should be able to produce that yourself. Why do we know that? Because by looking at A and C, we can determine that the F double prime was decreasing, at least in a certain range for the graph C. Like in this first part, it also was increasing, but it started decreasing afterwards, so that was bad. Okay, yeah, in general, we don't have to analyze the third derivative when we are studying the graphs of functions, but just by understanding what it means in terms of derivative of the second derivative, we are able to answer questions about it. But let's move on. Let's move on to optimization problems. I only have 2. And this is a box with general information. Remember how optimization works. You're going to have an objective function Often this is a multivariable function that you want to make as large as possible or as small as possible. And you're also gonna have some constraint functions between the variables. If this is the case, if you actually have more than one variable, first of all, use the constraints to solve for some variables in terms of just one other, like solve for y and z in terms of x. Because we are studying Calc 1, we can only analyze functions of one variable. Then you plug those variables into the objective, so you rewrite that as a single variable function. This should be your first step, if necessary. Now find an appropriate domain for this function using the information in the problem. For example, this x usually is a length of something or an area. It has to be positive. Then optimize. What does that mean? It means find the max or min value. Do we want the max? Be careful with this. Do we want the min or max value or point/location where it happens? Those are different things, right? Maybe if the function that you're optimizing is the area as a function of x, if they ask for what is the maximum area, that means the value, the a of x is the thing that you're looking for. But they may ask what is the parameter x that makes the area maximum. They're then asking about the point. All right, and then often you're gonna need to justify how you know that the min-max must occur, and also that it is the min or max. Remember that things like the first derivative test or second derivative test, they are only good enough to justify that a point is a local min or local max. But for these problems, you usually want it as a global, and it's gonna depend on the problem. We're gonna do it for both of these problems, so let's see how that works. Problem. Consider the region of the plane inside the first quadrant of the circle of radius 2 centered at the origin. Let me draw that. So you have a circle of radius 2 centered at the origin. This is x equals 2. This is y equals 2 up here. We're only looking at the first quadrant. Now, a rectangle is going to be inscribed inside the region with one vertex at the origin, one vertex on the x-axis, one vertex on the y-axis, and one more on the circumference. So here's a rectangle inside of this region. What is the maximum possible area that this rectangle can have? And then is there a minimum possible area? Okay. So how do we think about this? The function that we're trying to make max or min in this case is a function of two variables. It's the area, x times y. I just called x and y the dimensions of this rectangle. Those are the things that we can vary. But there is a relationship between x and y because this point is supposed to be on the circumference. X squared plus y squared, the coordinates of this point, they should be equal to 2 squared. 2 is the radius of the circumference. So if you solve, for example, for y here, y is going to be square root of 4 minus x squared. I'm taking only the positive root because y is positive in this problem, as you can see from the picture. So from this, we have now solved for one variable in terms of the other, and we can rewrite the area function as a function of one variable only. It is x times y. Just plug in this value for y. So it's actually x times 4 minus x squared. That's your objective function with a domain of, so here's the place where you have to have some freedom here. For example, do we consider x equals 0 to be a possibility or not? Imagine if x is 0 in this picture. That means there is no width to this rectangle. It would actually be a rectangle right here, a line segment. Do we call that a rectangle or not? It has area 0 for sure, right? So that's up to you. I'm going to consider yes. In general, we'd like to consider the endpoints as part of the domain. That makes the analysis sometimes easier. But this is up to you. So I'm going to consider this as well as what is the maximum possible value for x up to here, the number 2. Similar thing. If you include 2, what is the rectangle that has width 2 here? Well, this third point then coincides with the x point. It's this infinitely short. It's just a line segment again with area 0. Okay, so let's consider this domain. In this domain, what is the maximum for item A? A was asking for the maximal area. What is the maximal area that we can find? How does that work? You're going to need to analyze A of 0 and A of 2. We already know those just from the picture, or from plugging in 0 and 2 into the formula, you have the value 0. And then you also need to find critical points. A prime, set that equal to 0. So I'm going to just copy down A prime for this function. You calculate that by using the product rule. This is A prime. It's the square root minus x squared over the square root. Where does that equal 0? To find critical points, solve this equation. You move the fraction to the other side and then multiply, cross multiply to bring these square roots together. You're going to get 4 minus x squared equals x squared. And you solve this as x equals root 2. Only the positive solution, again, because x is positive. By the way, there is also a point where A prime does not exist if this square root in the denominator is 0, but that would be x equals 2. That's already being considered here anyway, so we don't really care about that. In terms of critical points, this is the only one that we care about. So we go ahead and calculate also area of root 2. Plug in x equals root 2 into the area function, which is up here. What do you get? So this becomes a 2. 4 minus 2 becomes 2. And this x is also root 2. So this is going to give you root 2 times root 2, which is 2. Okay. So now look at the values that you found. Those are all candidates for being the maximum or minimum value of the function A in that domain. What is the largest one that we found? It's the number 2. That's the max. So answer, maximal area is 2. Notice that item A was asking for what is the maximum possible area. They want the A value. They don't want the X value. The answer is 2. A, by the way, corresponds to a square. When X is equal to root 2, Y is also going to be equal to root 2. This rectangle is a square in that case. That's my horrible square right here. Okay, now item B. That's going to be quick. Is there a minimum possible area? That's what they were asking. Well, this is going to depend on your interpretation of the problem. These values that we just found, 0 for the min and 2 for the max, 0 happened when there is no rectangle, actually. These guys were corresponding to the situations where the rectangle became just line segments, like this and like this. Do you still want to call those rectangles? If you do, then you're going to say yes. 0 is the minimal area when the rectangle has no width or height. That is, if you consider those degenerate rectangles as rectangles. Or you can also say no if, like, let me say degenerate rectangles are not rectangles. That is the domain. If you consider the domain for X can only be between 0 and 2 without including them, then there is not going to be a minimum value, because what we have determined is that the function between 0 and 2, it tries to become 0 at 0 and also 0 at 2, and it has its maximum value at root 2. Well, root 2 is actually here. So this area function kind of looks like this. right? That there was a clear maximum value for area, but there is no minimum if you don't consider 0 and 2 to be part of the domain. Okay, this one is about a fence. A fence of height square root of 72 feet runs parallel to the wall of a house at a distance of 3 feet. So you're going to have a wall of a house. You have 3 feet here, and then some fence with a height of square root of 72. This is the ground here. Find the length of the shortest possible ladder that extends from the ground to the house, just touching the top of the fence. So imagine that you're going to put a ladder here. What you're free to choose is the locations where it touches the ground as well as the wall. And assume that the vertical wall has infinite extent, and also the horizontal ground. They both have infinite extent. So you're allowed to put these guys as far as you want. But of course, you're looking for the shortest ladder. Okay, so let's call the total height here y, and other variables that you can consider. Well, the y determines how tall this point is going to be, how high, and you need something that determines how far away from the base this point is. You can either consider this whole thing to be your x, or you can consider just this part to be your x. Doesn't matter. As long as it's clear in your picture, as long as it's understandable what you're doing, then this should be fine. I'm going to use this one as x right here. Okay. So the function that we're trying to find the shortest possible value for, or the smallest possible value, let's call that L for length. By the Pythagorean theorem, this is the function. We have a big right triangle right here with sides of y and x plus 3. The length is right here, the length of the ladder. This is the function that we want to find the minimum value of. But there's a hint that I mentioned, a suggestion during one of the lectures. Whenever you have a problem where you're trying to find the minimum or maximum value of a length function, like this one that involves a square root, it's often easier to do it for the length square. You define a new function, maybe I'm going to call it s for the square length. S is a function of x and y, but a very simple one without the square root. Why is this helpful? Because this function is much simpler. When you take derivatives here, you're not going to need to consider a square root. And after you find the minimum value for this guy, let's say we find 25, well, that is not going to be your answer. Your answer is going to be 5. You're looking for the minimum value for L. So even though the location, the value of x and y is going to be the same, where s has a minimum, L is also going to be at a minimum. But the value itself is not the same. The value is whatever it is for s, it's going to be the square root of that for L. Okay, so we're going to find the minimum value for s. First of all, this is a function of two variables. We need a relationship between x and y. We find that by similarity of triangles, right? Look at the large triangle. Let's do the horizontal over the vertical. You have x plus 3 divided by y. That should be equal to, let's look at the smaller triangle, just x divided by this height of the fence, which is square root of 72. This is going to allow you to write y as a function of x. Y is equal to root 72 times x plus 3 over x. So you go back here and you write s as a function of just x now. I'm going to write y squared. So take the square of this expression, 72 x plus 3 over x squared. This is the function that we are dealing with. What is the domain for this? So this time, maybe I'm not going to include the endpoint. X is clearly a positive number because it's a measure. It could be anything all the way up to infinity because we said the ground is infinite in this direction. You can put this point as far away as you want. But I'm not going to consider x equals 0 as a possibility this time. Because I'm going to say this letter certainly cannot be vertical. If x is 0, imagine for x very small, this would be almost vertical. And then if x is actually equal to 0, then there is a vertical ladder here that's just infinite, never touches the wall. So consider this function on this domain. We're looking for the minimum value. Well, we're not even guaranteed that it happens, that it exists, because this time the domain is not a closed interval. Remember, the extreme value theorem says that a continuous function on a closed interval, something like this, that function always has a minimal and a maximum. But because we have an interval like this, we don't know yet. In fact, this function is never going to have a maximum here, but it does have a minimum. And we can find that by looking at critical points. So there are no end points to analyze. We don't have to plug s of 0, for example. But we can try to find s prime. Turns out to be 2 times x plus 3 times 1 minus 216 over x cubed. Just find the derivative of this function. It's going to have a factor of x plus 3. As you can imagine, there's x plus 3 here and there's x plus 3 here. So do this by yourself. Now set this equal to 0. What are the possible solutions here? Either x is minus 3, which is not good for you because x has to be positive anyway. So only this other part is going to be meaningful. If you set this equal to 0, what do you get? Multiply by x cubed. X cubed equals 216, which is the cube of 6, by the way. This has a very neat solution, x equals 6. This is the critical point. So we know that an extreme value possibly happens at this location. Now, somehow we're going to need to justify that this is the global minimum that we are looking for. Minimum point in this case. There are a couple of things that you can try to do here to justify that. How do we know? Let me just put this into words. How do we know x equals 6 is global minimum point? Probably the easiest thing to do here is analyze the sign of s prime. What is going to happen to s prime before the number 6 and after the number 6? This part is always positive, that's okay. Now this part right here, let's say if we make x larger than 6, x cubed is then larger than 216, but this is in the denominator with a minus. This whole expression is also getting larger then. In other words, s prime is going to be larger than 0 after the number 6. And similarly, you can determine that it's smaller before. So whatever the value of s of 6 is, imagine the number 6 here, the function s has to be decreasing for every possible x before 6, and then increasing for every x after 6. So all the way from 0, the function has to start decreasing until it reaches the value that it does at number 6, and then starts increasing again. And I know that it goes off to infinity in both ends because of the nature of the problem. S represents the length square of the ladder. Remember that. So just imagine in this picture what is happening when you make, for example, x very large. That means you're taking this end of the ladder all the way to an infinite distance. That's causing the length to go to infinity. Similarly, when x was very close to 0, remember that was also a ladder that's getting larger and larger. So this is what the S function looks like. From drawing this picture, you can see that this is a global minimum value. But what is that value? S of 6. Just go back to the S function, and you're going to find the number 243 for that. This is the minimum value of the S function. Just remember that when we started this problem, we decided that we did not want to work with the length function. We wanted to work with the square length. We just found the minimum value for the square length. What is now the length minimum value going to be? Minimum L value is L of 6, just the square root of that. Be careful with problems like this. If you do this trick of replacing the function with a simpler one, well, then after you find the min or max value for it, go back to the original function. This is the answer to this problem. Lengths were given in feet, so you have to use the units of feet for this.